So the next type of reaction actually is just an extension of the double displacement method of solving for our reactions. And it's called an acid-base reaction. So that means you have to react an acid with a base. So in order to kind of recognize this, it's very similar to that of the precipitation reaction, where you have two salts that are actually reacting with each other. In an acid-base reaction, you have to recognize an acid reacts with a base. It still looks like salts, though. They still look like salts, because remember, an acid is named very similar to that of an ionic compound or a salt. So really, that brings up the question, what's an acid and what's a base? And as you start down this rabbit hole of a question, there's lots of different ways that you can define an acid and a base. These are the 7 common ways that you can define an acid and a base. In Chem3a, we concentrate on one of them. We don't concentrate on all of them. You won't really talk about all of them until you're much farther along in chemistry, upper division chemistry classes. So really the one that we're going to concentrate on is this first one here, which is Arrhenius behavior. And Arrhenius behavior really just says an acid is a substance that has a cation as an H+, so that when it dissolves, it donates that H+. So we can see that with all our acids, when we named acids, that the cation was always an H+. So that's how we recognize that that's a possible acid. The second part is that it has to dissolve in water, which means our physical state has to be AQ. So that's the reason why when we taught or learned how to name acids, we had to have AQ at the end, is because that acid can only occur when the cation is an H+, and you're dissolved in water, which means your physical state is AQ. A base is a substance when dissolved in water releases or gives off hydroxide, OH-. And so we can see in the previous example how the sodium hydroxide or calcium hydroxide or anything that's a hydroxide and aqueous would be a base. And that's going to be our definition that we're going to use for Chem3a to make our life a little bit easy. When you further your adventure into chemistry into 1A and 1B, we then expand it. We start to go farther and farther out. In 1A, we start to introduce the idea of Bronsted-Lowry systems, which again in 3A we're not going to worry about. And then in 1B, we actually worry about the Lewis acid-base system, which again in 3A we don't have to worry about. So we have a very easy time. When we're looking for an acid, we're looking for the cation of H+. When we're looking for a base, we're looking for the anion of OH-. If you have that, or hydroxide, if you have that, you probably have an acid-base reaction. And when you have this acid-base reaction, you can swap partners. So these are some common acids and common bases that we can see. Now, there are some other sets of acid-base reactions that don't look like acid bases based upon our definition. But because we have that table, and because we look at it and says, well, this acid, we still name an acid almost very similarly, or we put it together very similarly as that of an ionic compound, we can still use the double displacement method. So we're going to show those examples here and there. So here's one where we write the reaction between hydrochloric acid and calcium hydroxide. So we have HCl, we know that's AQ, and calcium hydroxide. So we look up calcium hydroxide. Most hydroxides, it depends on the table. Where's hydroxide? OH. Calcium should be, I think that says calcium. I can't, my thing's too messed up. Pretty sure that's calcium. Is insoluble, so this is a solid. So it looks at first that this can't react. But because this is an acid-base reaction, hydrochloric acid with an hydroxide, the acid can dissolve the actual solid. When this occurs, you're going to flip-flop your partners again. So my H+ is going to go with my OH-, right? That's going to create HOH, again, H+, OH-, 1 to 1, or commonly known as H2O water. This is called that neutralization reaction that we saw in the previous slide. The other thing that's going to happen is the other two are going to come together just like we did before. So our calcium is going to go together with our chloride. So those two are going to hook up. When this does this, we got to remember our charges. Calcium is positive 2, chloride's minus 1. And so I need 2 chlorides. HOH, water. Water dissolved in water is not going to be aqueous. You're just making more water, and water is a liquid if there's liquid water around. So its physical state is a liquid, L. That's our evidence of reaction. We made the liquid water. So we know that there's a chemical reaction here, which means we got to balance it. What about calcium chloride? Well, here's, where'd chloride go? Here's chloride, here's calcium, that's AQ, so this is aqueous. Now that we know we have a reaction, because we created a liquid, we can actually end up balancing it. And so that's easily balanced, again, by using your evidence of reaction. We have 1 hydrogen, 1 hydrogen, so that's good. 1 chlorine, 2 chlorines. So we're going to have to put a 2 on this side, which is going to change the chlorines to 2, but that changes my 2 H's. Now again, we got to be careful. I leave it as HOH because this is H plus, and I can just look at my H plus. I'm not going to count the H in hydroxide because that's my hydroxide group. In other words, I'm not going to break it up as H's and O's. I'm going to look at the cation H plus and the anion OH minus. So the cation H plus, I have 2 of them. I need 2 cations of H plus, which gives me 2 anions of hydroxide OH minus, which I already have 2 anions of hydroxide. So it's much easier to balance acid-base reactions by not writing it as H2O, but writing it as HOH, because you can look at the ions that are making up water. 1 calcium, and we have our balanced reaction. Trying to get you to another example here. We'll try that one. Hopefully I have it right here. So one of the things that your textbook will go into are these gas-evolving reactions. I didn't mean to skip it as much as that. And so it's talking about all this stuff that undergo gas evolving because it decomposes, doesn't like to stay around. There's energy given off, so it can decompose. Here's some examples. You don't have to memorize any of that. And you don't have to memorize any of this because I've given you all that information here. And we're only going to test on these ones that you create. So I'm not going to test on all the different versions. That's in 1A. So again, if we know it's an acid-base reaction and we take nitric acid reacting with sodium carbonate, we can look up sodium carbonate and that's going to be aqueous. Whoops, I didn't want to do that. Because remember, all sodiums, wherever the heck that went, are all aqueous across the board. And again, if it's hard to see this in the video, you're probably going to, like I said, you're going to print that out. Sometimes it does magnify a little bit better, but you're going to want to refer to that as you're watching this example. So this doesn't look like an acid-base reaction. Why doesn't it look like an acid-base reaction? Well, we can see this acid, but I don't see a hydroxide here. This shouldn't freak you out. It's still considered an acid-base reaction. But what you can do is you can recognize, well, wait a minute, cation, anion, cation, anion. I can use my double displacement method. In other words, even though we recognize this or we define this as an acid-base reaction, we're just going to use the double displacement method to solve it. So we're going to group up that cation with this anion. So those two are going to flip-flop partners, right? And when we do that, H is +1, carbonate is -2, so I'm going to need 2 HCO3. Now remember, we have water, we have H, it's going to be aqueous. Plus, then, our sodium, we don't care how many, is going to hook up with our nitrate. Sodium's +1, nitrate's -1. Oops. I don't want to do that. So it's going to go together directly. We look up, oh, that's right, all sodiums are aqueous, so this has to be aqueous. At first, it doesn't look like we made a chemical reaction, so I shouldn't balance this because we said, well, wait a minute, I have to make a solid, liquid, or gas to have a chemical reaction. I don't see a solid, liquid, gas. But remember that fourth one, solid, liquid, gas, or a weak electrolyte. And here is that weak electrolyte right there. Now, what's special about this weak electrolyte is during this reaction, it doesn't stick around. You want to get rid of it. It decomposes. And so what I recommend everyone to always do first is this is partially correct. So let's finish balancing it, and then let's get the real answer, right? So let's finish balancing this because I have 2 hydrogens. I only have 1 here, so I'm going to need a 2 out here. That gives me 2 nitrates, 2 nitrates, 2 sodiums, 1 carbonate, 1 carbonate. I have a balanced reaction now. What I want to do is I want to fix this because this can't stick around because it's a weak electrolyte. It actually decomposes in the presence of this acid-base reaction. Even though it doesn't look like an acid-base reaction in the way we're presenting it, it is. We can just use that double replacement method to predict it, even though we're not worrying about this method of acid-base reaction. We're worrying about Arrhenius behavior. So all that does is we just replace this substance, that carbonic acid, as it tells us with CO2 gas, there's our evidence of reaction, and liquid water, there's another evidence of reaction. And so all we do is we come back, we'll change the color, and we just say 2HNO3 aqueous plus Na2CO3 aqueous. I'm replacing my carbonic acid with CO2 gas. There's our evidence of reaction. And our liquid water, which is our evidence of reaction, plus 2NaNO3 aqueous. And so it turns out, and again, this is where all of those reactions that the textbook talks about, you have to memorize, you got to learn, you got to memorize the solubility table. You don't have to do that. It's all in here. I'm only ever going to give you something from these pages. So you don't have to sit there and memorize all that extra information. So really, you want to focus on being able to read this and utilize this. Acid-base reactions with Arrhenius behavior is very easy to recognize. It's H plus with OH minus. But you're still using the double displacement method. Acid-base reactions that use a different theory sometimes are a little more difficult because you're looking for that base or you're looking for that acid, but you don't have to worry about it too much because you can still use the double displacement method to predict the products because you get this. And again, you'll only get something like this. Oops, didn't want to do